All right, guys. So this video here, we're going to talk about Lewis dot structures and how they can help us with the bonding process. So all these notes that you see here on the screen are from previous videos. You want to make sure that you watch those videos if you need help with that stuff. But we're going to come way down here and focus on this. So a Lewis dot diagram, Lewis structure, whatever you want to call it. Let's get my drawing tool here. Drawing tool. Okay. So a Lewis diagram is a visual representation of valence electrons. Visual representation of valence electrons. Not to be confused with Bohr diagrams. These things here, those are Bohr diagrams. Bohr diagrams show all electrons. So I'm just going to put a little note here. Bohr diagram shows all electrons. And that's kind of why we don't like them, because if I'm doing like Mercury here, he has 80 electrons. So I'm going to have to draw these circles with 80 red dots around it. That sounds like a pain in the buns, and I don't want to do that. All that really matters are those valence electrons. And that's why we have Lewis dot structures, so that we can just have that visual representation of valence electrons. So let's remember our trick. If we go back to our periodic table, the trick is that if we look at the periodic table, the group number here, I'm highlighting it in blue, that represents the number of valence electrons for everything in that column. So boron has 3 valence electrons, magnesium has 2 valence electrons, selenium has 6 valence electrons, and we can always know the number based on that. So let's just draw one as an example here. Which one do we want to do? Let's do selenium. Selenium, Se. I don't think that was one that you guys had to know, so that makes it more fun. Okay, so selenium, Se, has how many valence electrons? 6. So the Lewis dot structure basically is dots that represent electrons, and those electrons are going to go around the element symbol. So I'm going to start by drawing one dot. 1, 2, 3, 4, 5, 6. Notice how I only put one dot at a time on each side. And once I ran out of room, once I had top, bottom, left, right, then that's when I was able to double up. Let's take a look at a Lewis dot diagram of one without that many. So let's try to do magnesium here, Mg. So magnesium, if you look at the periodic table, he has 2 valence electrons. He's right here, 2 valence electrons. So I'm going to go back. He's only going to have 2 dots. So I'm going to put a dot up top and a dot down here. Now, there is no right or wrong in terms of where those dots go, except for that they can't go next to each other. What I mean is that if you want to say Mg and put a dot here and a dot here, that's perfectly correct. Or if you want to do Mg and you want to put a dot there and a dot there, that's perfectly correct. Or maybe you want to put one on the left and one on the right. That's perfectly correct. What is incorrect is putting the 2 dots next to each other when you have all this empty space. So that is not correct. That's the only time, that you can't do that. So it doesn't matter where the dot goes. What's important is that they're just not next to each other until they have to be, like they do in selenium. And that's like pretty much it. That's Lewis dot structures. That's how you draw them. They're a representation of the valence electrons. We're going to add to this, though, a little bit. Let's go back down to magnesium, and we're going to see why they're so helpful and why they're so useful in terms of, the bonding and stuff. So looking at magnesium, he can either lose these 2 electrons to have his full outer shell below, right? Or he can gain 6. And we already decided from the last video, he's not going to do the latter. He's not going to gain 6. That's too much work. He's going to lose 2. Looking at selenium, well, I can see that all he needs is to fill these 2 empty spots in order to be happy. So when we have magnesium and selenium together, we can see really simply by just the pictures that this electron can go right here, and here we have a pair. This electron can go right here, and now we have a pair there. Selenium is happy with a -2 charge, right? Because he has 2 extra electrons. Magnesium is happy now with this +2 charge because he got rid of those 2 electrons, and they can go together and become magnesium sulfide or magnesium selenide. And again, this isn't important, that the compound that they make. What is important, what I need you guys to see, is just how easily we can, visualize that exchange. Even more useful, let's say we have sodium Na. He has 1 valence electron. I have that memorized, but you can look at the periodic table. Sodium, and then we have oxygen. Oxygen. And oxygen has 6 valence electrons. So if these two wanted to bond, well, I can obviously see, I know sodium wants to get rid of this one. So sodium can say, okay, well, here you go, oxygen. But does that make oxygen happy? Well, the answer is no. He needs another one. Sodium's happy. He's, yay, I'm happy. I have a +1 charge. But oxygen's still sad. And so what can happen is we can get another sodium. Oops, let me do it in a different color here just to keep things consistent. Another sodium with a valence electron, he can come along and say, I can be happy too if I give you one. And now look, oxygen, you're happy with a -2 charge. I'm happy with a +1 charge. This sodium's happy. We're all happy together. And when they go together, we have 2 sodiums and 1 oxygen, and that becomes Na2O, sodium oxide. Woo! Again, not important right now. We will get there. But what is important is, again, this visual that we get out of this. So while you are not going to be responsible for drawing these and making these connections, it just basically reiterates the importance of those Lewis dot diagrams and the use of those. And it just helps bring everything that we've been doing together. It shows you where the oxidation number comes from. It shows you how those valence electrons come in, and it lets us avoid these Bohr diagrams that are a pain in the butt to draw. So that is valence electrons, Lewis dot diagrams, and oxidation numbers all wrapped up.